Our next speaker is Ezekiel Oyeniyi, and he's going to talk about pseudopotential for orbital free density functional theory. Okay, you can get started, as you see.
All right. Sorry. Yeah, so I'm Ezekiel Oyeniyi from the University of Ibadan, Nigeria. Yeah, so I will talk on pseudopotentials for orbital free DFT. Yes, so we know that Consham DFT, it's a widely used approach for modeling materials. And of course, a good compromise between accuracy and computational cost. However, it scales cubically with the size of the system. And this makes it computationally expensive for large systems like the quantum dots, proteins, and complex system interfaces. And so there's a need for alternative approach to handle such large systems. And we have a number of approaches, which include the orbital free DFT. We have the density embedding and the machine learning approach. And for example, the orbital free DFT follows from the Consham DFT, where actually the fermions and non-interacting fermions are matched to interacting fermions via the exchange correlation. In the embedding approach, here the system is fragmented into smaller sizes, and Consham calculations is performed on them, and this is put together with the equation below. And then, of course, machine learning is another approach which can be used to learn different properties of the system, including electronic structure property. So our interest is the orbital free DFT, which the energy functional is given as this, and with this approximate kinetic energy density functional. And because it is purely energy density functional, we minimize the energy functional relative to density to obtain the ground state density. And if we have used, depending on the kinetic energy density functional used, this approach can scale linearly and could be used for large systems, like, for example, the quantum dots. In material science, we use plane waves in our calculations, and so for that reason, there's a need for pseudopotential approximations, where the inner core electrons being replaced by a non-local pseudopotential. And so when we talk about pseudopotential, there's always the local and the non-local part. And for the orbital free DFT here, we're actually using a plane wave. And so definitely our potential, the Coulomb potential here is a pseudopotential. It's approximated as a pseudopotential. However, it has no non-local parts. Reason because it's hard to couple the density to the non-local parts. And so what it uses is only the local parts of the pseudopotential. Yeah, so there are current state-of-art method for generating pseudopotentials for orbital free DFT. One is taking the non-local parts of the Concham pseudopotential and use it right away in orbital free DFT. Well, over time, it has been discovered that this is an inaccurate method. Other approach is to create one body reduced density matrix and couple it with the non-local parts of the pseudopotential. This was implemented by Zhu et al. 2022 and found that there is this mixed result. It's not really great. And then another approach to generating pseudopotential for orbital free DFT is the Concham inversion, which was implemented by here. So the Concham inversion, this has to do with reproducing Concham non-local pseudopotential properties with Concham local pseudopotential properties. So if this is fine, then you can just straight away use the Concham local pseudopotential in the orbital free DFT. However, there's a flaw with this approach, because then the difference in the exact kinetic energy functional and the approximate kinetic energy density functional is not captured. And so our motivation in this work is to correct for this difference, and to include some effects in the local pseudopotential. Yeah, so an improved design for local pseudopotential is as follows. This is our approach. So our target is the non-local pseudopotential from and its pseudo density with an approximate kinetic energy density functional. And so we start by imposing. The energy functional from Concham to be equal energy functional, or to be equivalent to energy functional from orbital free DFT. And by implication, this is showing to us from this next equation that the exact kinetic energy functional approximates the approximate kinetic energy density functional. Also, the local pseudopotential from orbital free DFT approximates the non-local plus the local pseudopotential from Concham. And so when we invert this, we have this correction. And in the correction, we find this capturing the difference in the exact kinetic energy functional and the kinetic energy density functional. Also, it incorporates the effect of non-local part of kinetic density functional. So to implement this, so what we have done is, to approximate our correction, which we have just shown. So what we start by is to impose that the correction is actually spherically symmetric. And we went further to express our correction as a fifth order polynomial with this user-defined radius cutoff, and then subject it to this boundary condition, which is actually a short-range boundary condition. And we obtained these parameters and found that the A0, A1 vanishes. And then we have this A2, which depends on A3, A4, A5. And so we have to optimize these parameters A3, A4, A5 in order to minimize the difference in the density of orbital free DFT and the consham DFT. And this optimization was implemented, using the Thomas-Fermi kinetic energy density functional as implemented in DFT pi. So this we found. So we tried this for transition metals, and this the PGBRV 0.2 is the new pseudopotential we obtained, and the GBRV is the local part of the consham pseudopotential. And so we found that this plot is comparing the densities relative to the consham density, and we found that the new pseudopotential gives a better comparison to the consham density. Yeah, so using another type of pseudopotential, I mean consham pseudopotential called PSL, we still found the same trend. Our new approach, which is the PSL 0.2, is showing a better result relative to the consham DFT. We also perform, so with this new pseudopotential, we performed calculations for, EOS, equation of state parameters and phonons. And we have done this calculation using different pseudopotential, including the new pseudopotential obtained. And we have used different functional, though we have actually optimized our parameters. We've gotten the new pseudopotential using just the Thomas-Fermi 0.2 von Weizsäcker functional, but then we have to test with different functionals, the same pseudopotential. And we found that looking at the table, this is for silver, looking at the table, we found that the new pseudopotential has, so our reference actually is the consham GBRV. This is the consham results. And then comparing this with this, so we found that our new pseudopotential gives a better result with compared to other pseudopotentials. This we also found with the bulk modulus. When we come to the palladium, the same trend was observed, the new pseudopotential giving better results. And we can also say that here that our new pseudopotential is transferable over different functionals and different phases of the system. We did a calculation, for the phonon. The blue lines shows the phonon from the consham local pseudopotential, and the red line, so the red line shows the reference, that is the phonon from consham, and the black line is the new method. So this, we can see that the new pseudopotential compares well to the consham, the reference, the consham approach. Then we extended this pseudopotential to calculating densities for clusters. So we have picked for silver 20 and palladium 13. And this is showing that our density, the density produced by our method compares better to the concham, because here, for example, here is 0. So we are away from the concham density by 0.042, but for the local GBRV is 0.182. So here we see that our method performs better than the local GBRV. The same we could see with palladium 13 cluster. And so I say, so this is where I'm going to stop. So thank you to Professor Micheli for the opportunity, and thank you to Valera. Thanks to Sunday. Sunday is in Kigali. Thanks to Okelo. Okelo is in Uganda. And thanks to Wala. So we have all worked together to make this happen. Thank you very much.
Okay, so any question for Ezekiel?
So at some point you showed an expression for the difference in potential between the two methods, and they involve functional derivatives of this one exactly the equation at the bottom. So
Yeah.
of course the dTs by dn, you don't know what Ts by dn is, right? Because you don't have the explicit function. Are you using this formula explicitly, or are you expressing that in different ways?
Yeah, so this we are expressing directly. This is actually the exact
Well, it's
kinetic energy functional.
It's the formally exact expression, but what do you do in practice?
Okay, so in practice, this is dependent on orbitals.
Mm-hmm.
Yeah, so this is dependent on orbitals, while this is purely dependent on density.
Ezekiel, if you go to the next slide, I think we can answer this question.
Okay.
Yeah, so in practice, you just simply find this correction, this delta VLPP, by minimizing the difference between the orbital free density and the concham density.
So you don't evaluate it in this.
We don't evaluate it with that, but we just do like a Wu Yang like VP for that to find this delta V.
Okay, yeah.
Mm-hmm. 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 So then you have this polynomial expression,
Right.
and you find, of course, A0 is irrelevant because that would be a constant in any case.
So this will impose this VLPP to be like spherical around the atom. So this inversion, this is effectively an inversion, will not be perfect. Because we don't allow this delta VLPP to go everywhere in the cell. So Ezekiel, can you go to the next slide? Yeah, so you see, this is a percent deviation from concham. We would like it to be 0, but it's never gonna go to 0. So it's going to like maybe 10% for niobium, and for zinc is really going to 0. So you have like a kind of like the green part is what we say, okay, you can pseudize those atoms. The red part, the red areas, we are kind of on the fence. And the blue part is like, don't use this, don't use them. You cannot access them. Yeah, no.
These elements here are, I mean, what?
Yeah, so the chemistry, what makes them
why are the green
Right.
ones better than?
And we wondered ourselves, and I don't know, we came up with some thoughts, but nothing that is conclusive. Like if there are a lot of unpaired electrons in the atom itself, then it's harder to pseudize. So like iron is hard, group 10 is hard, titanium is hard, scandium is hard. If you have unpaired electrons like that, but if you have more d electrons, it's easy. So all the atoms with more d electrons, it's easy to pseudize.
Difficult to say.
Hard to say, yeah.
Yeah, does it have to do something with the the structure itself?
Maybe.
Maybe, but they're usually, I mean, these are all metals, right?
Yeah, we
They
used like
tend to
the
be, they tend to be whatever these
PCD,
do. Yeah, so it's
we-
not structure.
Unlike.
Which functional is it based on?
For computational reasons, we use the Thomas Fermi von Weizsäcker functional
Ah,
and the Thomas Fermi point two von Weizsäcker functional. So we have two functionals.
but and for exchange correlation, you don't.
We just use LDA, but we suspect that that's not really the big issue here. The
Oh,
issue is the kinetic energy.
So you think that if you did a different functional,
You
you're
don't
also
get
get
the same result, yeah. Yeah. Well, I mean, considering that there are no pseudopotentials for transition metal elements for orbital free DFT,
I mean,
this might be just about the best we can do today. Yeah.
This is already amazing.
I don't know if it's amazing, but certainly they worked super hard and
These are after iodine, right? Like most of these elements.
those transition metals, yeah.
So, like, what about relativistic effects?
Yeah, so in this particular case, they are accounted for at the scalar relativistic effect. So we don't have spin orbit, but there's a scalar relativistic effect that kind of takes into account the fact that in the core, the potential is, effective potential is kind of different. It's not really a Coulomb potential. But beyond that, we don't have.
Okay.
But it's not, you don't include magnetism.
There's no spin.
You got cobalt and you got nickel in there.
Yeah, there's no spin here. We don't even have a code to effectively to speak correctly, like we don't even have it. So that's,
Can you make it?
you and Igor Madzin are asking me this.
I'm
and
sorry.
do
I'm
it.
sorry, I lost it.
Yes, yes. Maybe even non-colleagues, yes.
Well, okay, let's not go ahead of ourselves. Yeah.
Okay, so
So, I'm sorry,
Yeah, go ahead.
and now that you have these pseudopotentials, what will you do with them? What do you have an application that you have in mind? What is your dream?
Ezekiel, what's your dream for these pseudopotentials?
Yeah, so we are already creating a table. I mean a periodic table for this. So that anyone who will want to do some calculations could just assess this pseudopotentials. So this is one of the things. Maybe Valeria could help to comment on this.
So essentially Ezekiel's dream is that people just use them. People use this.
For example, you could do clusters, right? I mean,
Yes.
gold clusters, gold nanoparticles. There's a huge industry that looks into gold nanoparticles and all kinds of other things mixed. I mean, you could put alloys, these
High
core
temperature, maybe
shell quantum dots,
Core
and
shell, yeah,
whatnot.
so,
I
yeah.
mean,
quantum dots. So low temperature, we can do quantum dots. High temperature, we can even look at the structure of high temperature.
what can you do? You could do plasmonics, of course, right?
Interesting. You mentioned that. So Valeria, I don't know, Valeria will talk to us about that.
Good.
Thank you, Ezekiel.
Yeah.
And physical